The last topic in this section is solving logarithmic equations. Um, in this section, we are going to solve pretty simple logarithmic equations, and then in section 6.6, we will come back to logarithmic equations. Section 6.5 is going to teach us some tools that we will need to solve more complicated logarithmic equations. So that's what we will do in section 6.6. So for right now, at the end of section 6.4, we are going to learn how to solve some pretty basic logarithmic equations. And then, like I said, they will get a little more complicated in section 6.6. Okay, so what a logarithmic equation is, it is an equation that contains a logarithm. Okay, like I said, the ones we're going to do right here are pretty basic. So in the second bullet, it tells you we can solve some logarithmic equations, the basic ones, by applying the definition of a logarithm and the properties of logarithms discussed so far. We will solve more complex logarithmic equations in section 6.6. Okay, this third bullet point, it's not going to matter so much in this section, but I want to bring it up now. It is very important to check your solutions when you're solving a logarithmic equation. Okay, basically, and like I said, it won't be an issue in this section, but in 6.6, where you're having the more complicated equations, it is definitely going to be an issue. You may get a solution that looks like a solution, but when you plug it back into the original equation, it causes you to take the logarithm of a negative number or of 0. And if that happens, you have to get rid of it. It can't be a solution. You have to exclude it from the solution set. Okay? So, like I said, I'm not going to worry about that right now. Everything in example 7, whatever we get as a solution will be a solution. It will work out. You will get examples in section 6.6 where something looks like a solution, but when you check it out, it doesn't actually work. Okay, so you might be wondering, well, how do I know when I should check my solution? Okay, good rule of thumb is if it's a logarithmic equation, you need to check your solution. Okay, like I said, I'm not going to spend the time on example 7 doing that because I know for a fact they all work out. Okay, and I want to concentrate on teaching you the basics of how to solve a logarithmic equation. Okay, when we get to the more complicated problems, we will go through each one and check the solutions. Okay, as far as exponential equations go, you don't have to worry about that. Exponential equations, the domain is all real numbers, so whatever you get as a solution, you should be able to plug in. Okay, so really only if your equation involves a logarithm do you have to worry about checking your solution. Okay. All right. So in example 7, there's a whole bunch of these. Okay. They are very basic equations. So you're going to have an equal sign and a logarithm of some base. Okay. You're looking for the value or values of x that make each a true statement. Okay. And all you really need to do is use the arrow thing to do this. Okay, so let's read the directions. I'm going to explain what those mean, and then we'll start solving. So in example 7, we're going to solve each equation, express irrational solutions in exact form, no decimals, and as a decimal rounded to 3 places. Okay, what this whole thing about an irrational solution means, you may get a funky looking answer for some of these. Okay, your answer might involve like a natural log, it might involve a square root, something where if you put it in the calculator, you're going to get an ugly decimal. Okay, so when that happens, you're going to have to give both an exact answer, meaning no decimal, and then also give the decimal form rounded to 3 places after the decimal point. Okay, so you'll see what I mean as we do these. Okay, so here's the first one. In part A, our equation is log base 5 of x is equal to 3. Okay, so again, you're trying to figure out what value of x makes that a true statement. Okay, so all you have to do here is you've got a logarithm equal to some number, you just have to apply the arrow thing, okay? This means if I take the base and raise it to this power, I'm going to get this, okay? So 5, an equivalent statement to this logarithmic statement is 5 to the third power is equal to x, okay? And then you just have to figure out what 5 to the third power is. That's 5 times 5 times 5 is equal to x, okay? If you multiply that out, 5 times 5 is 25, times 5 is 125, okay? That's the answer. That's it, okay? These basic logarithmic equations, you just do the arrow thing, okay? All right, next one, okay? Log base 3 of 3x minus 2 equals 2, okay? Again, if I take the base 3 and raise it to the second power, I should be getting this entire quantity, okay? So an equivalent exponential statement is 3 squared is equal to 3x minus 2, okay? And now this equation is easy to solve. We got rid of the logarithm, okay? 3 squared is 9 equals 3x minus 2, okay? And then isolate x, so add 2 to both sides, okay? We're going to get 11 is equal to 3x. Divide both sides by 3. Our answer is 11/3. Okay. All right. So 11/3, you might be wondering if that's irrational or not. Okay. You can look at the decimal approximation here. There's 11/3. Okay. Irrational means that you have a decimal that does not end and it does not repeat. This is a repeating decimal. Okay, so it's 3.6 and the 6 repeats forever. So this is considered a rational number. Okay. Basically, rational means fraction. If you can write your answer as a fraction, you're okay. Okay, so this is not an irrational number. Okay, so you can just leave it like this. Okay, if you're not sure, just put the decimal approximation out to the side. Okay, so that's the answer to that one. Okay, so moving on to the next page. Okay, like I said, we're just going to do a bunch of these. The more practice, the better. Okay. All right, so in example C, okay, here's our equation. Okay, little bit different here. The variable is the base. Okay, doesn't matter. It's still going to work the same way. Okay, you turn this, do the arrow thing and turn this into an equivalent exponential statement. Okay, if I take the base and raise it to this power, I'm going to get this. Okay, so x to the third power is equal to 1/8. Okay, now you've got to solve this for x. Okay, so to undo the third power, we're going to go ahead and take the cubed root of both sides. Okay, so remember, cube and cubed root cancel. Okay, if you're not sure how to handle this, anytime you have a square root, a cubed root, a fourth root, whatever, and you have a fraction underneath, you are allowed to make it the cubed root of the, or make it the root of the top divided by the root of the bottom. So in this case, you can break this up into the cubed root of the top divided by the cubed root of the bottom. Okay, so then the cubed root of 1 is 1, and then the cubed root of 8 is 2. So the answer is 1/2. Okay, so the base there that you're looking for, okay, 1/2 to the third power is 1/8. And you know, you could check these. That's the great thing about equations. Any kind of equation, you can always check your answer. Okay, remember, this means if I take the base, which is according to our answer is 1/2, and I raise it to the third power, look what I get. This is 1/2 times itself 3 times. Okay, multiply the fractions across the top and across the bottom, you're going to get that quantity 1/8, so you know you're right. Okay. All right. Part D is different, okay? It's got a natural log, okay? You could do the arrow thing on this, okay? And I'll show you that because that's what we've been doing, okay? It's not written, okay? There's no little subscript here, but you know that with ln, the base is e, okay? So you can write it in and then do the arrow thing, okay? This is saying if I take the base and raise it to the 8th power, okay, I'm going to get this entire quantity e to the negative 2x, okay? That's what this is saying, okay? The logarithms are now gone. You're left with an exponential equation, okay? So remember what we did when we solved exponential equations, okay? You need to have the same base on both sides, which we do. Both of these are base e. And then once the bases are the same, you can go ahead and equate the exponents. Okay, so we get 8 is equal to negative 2x. Then if you want x, you just need to divide by negative 2. And so you're going to get that the x value that works here is negative 4. Okay, so that's one way you could have done this problem. You can still do the arrow thing on it. Okay, now here is a second way that you can do this. Okay, so I'll go ahead and write method 1. Both should give you the same answer. Okay, it's just a matter of preference. Which way do you understand it better? All right, so here's method 2. Okay, so I'm going to go back to the original problem. Okay, natural log of e to the negative 2x is equal to 8. Okay, so I'm solving this guy. Okay, when we first talked about natural logarithms on page 3 of this packet of notes, we went through properties of natural logarithms. Okay, and we looked at this particular property, the third one here, where we said if we had the natural log of e to a power, okay, natural log and e are inverse functions, okay? If they're side by side, they're going to cancel out and the exponent comes down, okay? So that's exactly what you have going on here, okay? Natural log and e are side by side, okay? They are going to be inverses and cancel each other out, okay? And then the exponent would come down, okay? So you end up in the same place you ended up if you use the arrow method, okay? So this is just a little bit quicker, okay? So then you would go ahead, divide by negative 2, and again get x is negative 4, okay? So both methods work. It's just a matter of personal preference.